Okay, so good afternoon everyone, and let's start with a recap of what we had done last time. So last time we had a quick recap, quick overview of some aspects of quantum mechanics, and so here I have collected the highlights from it, which we will need quite frequently. So one is the simply Fourier transform. So Fourier transform. You can write a function of position into a function of case, and similarly you can reverse. So this is the Fourier transform formula. Any function f of x can be decomposed into this e to the power ik dot x modes weighted by some function f tilde of k, and then f tilde of k, any function f tilde of k can be written as a linear combination of functions of x. And the convention we use is that there is a 2 pi factor here. So there are different kind of conventions people use. We are going to use the one where the momentum space inverse Fourier transform has all the factors of 2 pi. And here this is a general d-dimensional Fourier transform. One could write a 1-dimensional Fourier transform, 2-dimensional, 3-dimensional. We just written d to signify that this is a d-dimensional Fourier transform. We can have different dimensions. Mostly we will have work in 4 or 3 dimensions in different cases. Then we also derived this formula for, so let me first write in 1 dimension for the Dirac delta function. We saw that the Dirac delta function is in 1 dimension is just this function. If you integrate it, you will get Dirac delta. It doesn't look so, but it is so, and we proved this by taking Fourier transform. So this k goes from minus infinity, and we can write the d-dimensional Dirac delta as just by increasing the dimension over here, dot x minus x prime, and this dot. So here when I write k and x, this is not just one coordinate. I'm being loose with the notation. I should probably give some symbol to denote that this is a vector, but please just understand that unless from the context that this is a vector which will have various components. So x means x, y, z, all of these, which we write as x0, x1, x2, xd minus 1, and similarly k is k0, k1. When I talk about special relativity, those of you who are not familiar with 0, 1, we will talk about it. Okay, and the next thing that we saw was the idea of Schrödinger and Heisenberg pictures of quantum mechanics. So as I was saying last time, what we would measure usually is some kind of a expectation value of some observable. So let's take the position observable x, and then something that we would measure usually is this expectation value. So we take measurements of x and we compose this expectation value. And generally what will happen is this will change with time. I take a electron, let us say, I measure its average position, and then 10 minutes later I come and again measure. I will see that the electron has moved. Most likely it is, suppose it's some electric field or something, it will have moved. So there are two ways to describe this change with time, and one is by saying that, so what we are observing really is this guy change, and there are two ways of describing this change. One is by saying that the state changes. So every electron has a state, or every particle has some state, and that state changes with time. And so then how does that state change is, so this is some state at t naught, and at a later time it becomes some different state t, and the way it changes is given by the Schrödinger equation that tells you the rate of change of the state given the external environment which is encoded in the Hamiltonian. So this is how the Hamiltonian, whatever it is interacting with, changes the state. and then this equation you can integrate this equation and you get this. I mean, this equation, as I was saying last time, is very simple. It looks like dx dt multiplied by some hx, and this is dx by x h dt, which gives you x e to the power h t type of solution. And so that is the kind of solution you get here also when operators are involved, and this is the solution you would get. Okay, and so this whole operator is something that we call the time evolution operator, u t t naught. This is the name for this, e to the power minus I h t minus t naught. This is the operator that gives your time evolution. It takes a state that at a earlier time and output as a state at a later time t. So this is one way of thinking of how things change with time, where the state changes with time as per this operator. The other way of, so when I write this this guy, how it changes with time, I have this. This is the u. So this is u. Then this will be u dagger. So psi going to u means that it's dual. Psi goes to u psi implies that this goes to this dagger, and so this guy, the expectation value, has two psi's here. So this is so this is psi t x psi t, and this is not u x u t t naught. So this is the Schrodinger picture, and the other picture is the Heisenberg picture, where we say that the state does not change with time at all. It is the operator x which changes with time. So this is called the Heisenberg picture, and here, so we are going to Heisenberg picture. So here the operator x, the state psi, does not change with time. It is independent of time. Psi does not change. So psi t naught, psi t, it's the same. It is never changing. But the operator x, which was not changing in the previous thing, now all the time dependence is here, and we write this as u t naught x u t t naught. So if I define it this way, you see that this guy has the same time dependence either way, whether I use a Heisenberg picture or Schrodinger picture. In one case I change psi, and in the other case I keep psi the same, I change x. I always end up with the same kind of time dependence. Okay, so usually we are going to put h here to denote we are talking about the Heisenberg operator. So this is at t naught. Okay, and usually what we will do is we will use some reference time when the Heisenberg and Schrodinger are the same, and then xh is usually, so let's say I put the reference time at 0, and then this is just the Schrodinger operator, and I have u. So I got t, I put t naught as 0. Okay, any questions? Okay, so today we will study the simple harmonic oscillator, which we'll see is the very important system for is going to be very important for this course. Okay, so the classical simple harmonic oscillator, I think all of you know, it's some oscillator, some system like this, maybe a ball attached to a spring which is oscillating or something, and classically it has this equation of motion which has solutions that look like this. Okay, this is the simple harmonic oscillator equation. Okay, and then yeah, excuse me. So the quantum mechanically, the Hamiltonian looks like this: p square plus half m omega square x square, where p and x are operators. And remember, in quantum mechanics, x and p operators have the following commutation relation. Okay, xp is equal to I into Planck's constant. So this is the commutation relation we have, and this is the Hamiltonian for a quantum harmonic oscillator. Now the simple way of solving the quantum harmonic oscillator is introducing these operators, which are called the ladder operators in quantum mechanics, and the creation annihilation operator when we study quantum field theory. So this ladder operators, we introduce these two operators, and why? Because if we calculate because they are very useful, as we will see. So if we calculate the commutator of these two, let's do that. So multiply these two, and we have m omega 2h bar x plus I by m omega p x minus I by m omega p. So what is the commutation of x and x? 0, and p is also 0. So the ones that survive are x p, so this is minus I m omega x p, and the other one is I m omega p x. Now px commutator is just minus of xp commutator. So we can write this whole thing as minus m omega by 2h. M omega cancels, so I just have I 2h, and there are two of these, so 2I x p, 2 and 2 also cancel, and this is nothing but minus I by h multiplied by IH, and so this is 1. So A dagger commutation is 1. We can also write x in terms of A and A dagger by subverting this. So x will be just this, and similarly you can find p also. So p will be is what we will get if you subtract these two. So then you have 2I m omega p as this, so that becomes 2. Okay, let's just do this. If I subtract these two, I get square root of m omega by 2h and 2I m omega p, and so then this becomes square root of 2 by m omega I will be there into p. So this is square root of m omega by 2 and minus I. So that becomes I into A dagger minus A, something like this. Okay, you can check. Oh, sorry, I have missed H cut, which was here. H cut. Okay, so we can invert this relation also. Now the Hamiltonian, if you substitute this x and p that I just wrote here, you will find that the Hamiltonian looks like this: A dagger A plus half, H omega A dagger A plus half. So substitute to find. Okay. Now we introduce something called the number operator. Number operator n, which is defined as A dagger A. So the Hamiltonian and number operator are just simply related: h bar omega n plus half. So this is the Hamiltonian in terms of what I have called the number operator. Why it's called number operator, it becomes clear very soon. But let's take this commutation n A dagger. So then that is nothing but A dagger A into A, and which is A dagger, which is A, which will become A dagger A, and A dagger and A commutation is -1 because A dagger was 1, so A dagger is -1. So this is minus A, and similarly this is A dagger. This is something you all know, but we're still going through this. So now consider the eigenstates of the number operator, and we call the eigenvalues, denote the eigenvalues as small n, eigenvalues as small n. So this is some eigenstate, and let me give it the name also as n. This is the nth some eigenstate labeled as n, which has eigenvalue n. And so then if we put n A dagger n here, what will we get? So n A dagger n is using the commutation relations A dagger n plus A dagger, using the commutation relations n, and so A dagger acting on n is, so this becomes sorry?
So it's n plus 1 into A dagger into n, and thus A dagger n is actually an eigenstate of n k plus 1.
Yeah, so what do we get finally?
N plus 1.
So we get here that this is n plus 1 into A dagger n, right? Because this whole thing is n plus 1 A dagger n, and n acting on this gives me n, and the whole thing gives me n plus 1. So n plus 1 A dagger n. So this is A dagger n is also an eigenstate of n with the eigenvalue n plus 1. So it increases the eigenvalue by 1 when I act with A dagger, and similarly when I act with A, it decreases the eigenvalue by 1. So I get, this is A n. So these operators, the ladder operators, what they do is they increase and decrease the eigenvalue of the number operator by 1. And by the same logic, they also increase and decrease the energy eigenvalues, because the energy operators are just n plus half, which means that the energy eigenvalues, because these two operators commute h and n, they have the same eigenstates, and so this is h omega n plus half. These are the energy eigenvalues. And so what these guys do is the action of, so if these are the energy levels, or if these are the n levels, these are the eigenstates of n and also eigenstates of h, denoted by numbers n. So what these guys do is the creation operator will take me from one energy level or one number level to the next, whereas the other ladder operator, the annihilation one, the A, will bring me down from a upper energy level to one energy level down. So what happens if I keep bringing it down, down, down? At some point, we will encounter a state with the lowest energy beyond which it cannot go. So at that time, so the ground state, which we call 0, ground state, is the maximum you can bring down, and after that it will go to 0. So the ground state is defined as the one where A0 is 0. So this is killed by the A operator. After that, this is 0. So this is the ground state. This also has n is equal to 0, because remember, this is the n operator is A dagger A. So if A0 is 0, A dagger A0 is also 0, because first the A acts and gives me 0. So this guy has 0 eigenstate, 0 eigenvalue. So this is the n is equal to 0. So these are 0 numbers of excitations, and then we have 1 excitation, 2 excitations, 3 excitations, so many excitations above the ground state. So this is how we solve the simple harmonic oscillator. You see, it's a simple system where each energy level is equally placed. So the difference between each energy level, any En plus 1 minus En, is always what? H omega. So every state is has this H omega energy level, and even the lowest energy state, n is equal to 0, does not have 0 energy, because you see you put 0 here in this equation and you get half H bar. So n is equal to 0 has energy H omega by 2, and each step above just goes as plus 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 of 1. So this system is the simple harmonic oscillator. Any questions? Okay. So now let's, the last thing we'll do today quickly is to just look at the simple harmonic oscillator in the Heisenberg picture, how it looks. So now again, as I told you, we define the Heisenberg picture excuse me, where the operators are no longer station operators, also change with time. So the Heisenberg picture operators of x and p will be related to the Schrodinger picture x and p, which don't change with time. So by fixing some t is equal to 0 when all operators are same, and then we say that at some time t the Heisenberg operators are given by this equation, whereas the Schrodinger picture obviously does not change. And then the Heisenberg equations operators are given by the equation of motion. This is the equation of motion for any operator. So for any operator in the Heisenberg system, it has to follow, instead of Schrodinger equation, it follows the Heisenberg equation of motion. So any operator dO dt in the Heisenberg picture is given by IH OH. Okay. So for example, what about the dx dt here? Dxh dt equals I H X H, and what is that? H is, remember, what is H? X square, p square by 2 plus half m omega square x, which part commutes with this? M omega square xh into xh. So this is nothing but I p square xh, and what is this? So this is 2 IH bar P by 2. So this is IH. Huh?
There's one more I outside of it.
There was one more I outside, and so this is minus H bar P. So this is dxh dt plus H bar P equals 0, and similarly dp dt will have a similar equation, right? So we have the same because this is symmetric in p and x, right? So this will be I think plus m omega square x equals 0, something like this. And so if you take second derivative of this, you will find that d2x dt2, and using this to replace the other guy, you will find that this will have, I think, a minus sign, and so you will find that an equation like this. M will cancel out, you will get m omega square x equals 0. This is the Heisenberg equation of motion you will get from these two equations, which the reason I write it is it's the same as the classical equation of motion that we had written down over here, except that these x's are going to be replaced by the hats, the operators. So this operator satisfies the same classical equation of motion, in this case at least, in this simple case. Okay, But we are concerned with this creation annihilation, these ladder operators, and so the ladder operators similarly satisfy this equation. And the ladder operator, it's simpler to work with ladder operators because we already know what this commutation relation is, because we calculated it for n, remember? And so the same thing holds for h also, right? Because n had just h omega outside and a plus half, which is a number which always commutes with any operator. So this is n, if n a is a minus a, then h a is nothing but h omega multiplied by this. So this h omega gets multiplied, and so this is minus h omega a, and h a dagger is h omega a dagger. Just multiplying h omega with the commutation relations with n, because that's the only factor that is there. So we have dAh dt is I h omega ah, and so then you can solve this differential equation to get ah equals what? E to the power I h omega t, and similarly the other one a dagger, this one, sorry, there was a minus sign here because minus, so this is minus, and a dagger is I h omega t. Okay. And so these are our how the AH and AH bar evolve with time. AH t, and this is A at t is equal to 0, and similarly this, and as A dagger. So these A and A dagger are the t is equal to 0, the Schrodinger picture things, which was at t is equal to 0, and these guys evolve like this. And so x h, for example, which we had written down as a combination of like this, so this becomes, in the Heisenberg picture at time t, is h by 2 omega multiplied by e to the power minus I h omega t a plus e to the power I h omega t a dagger. Okay. And so why I write this? Because this also looks very similar to the classical solution that we had here. So this was the classical solution for x. Some e to the power I omega t factor, e to the power minus I omega t factor, and here also we have pretty much the same kind of thing. Okay, pretty much the same kind of thing. There's a h bar here, which maybe should not be here, because I think there's a 1 by I. It's probably I by h bar over here. I have to check, and if so, this h bar should get cancelled. So this h bar persisting is, I'll check. But the form is the same, and this is how the thing looks like in Heisenberg picture. The reason we show this is when we do quantum fields, we will need the Heisenberg picture. We will work in the Heisenberg picture, and we will work with the simple harmonic oscillator also in the Heisenberg picture. Okay, so let's see how am I doing for time, because this is pretty much what I wanted to say for today. Sorry. Okay, I still have 20 minutes left. So what do I want to do? I want to talk a little bit about quantization, and maybe next time I will give more examples, but just quickly an overview of what does it mean to quantize a system. Okay, so we study quantum mechanics and we study classical mechanics, but one question you should have been asking is that how do we go from a classical system to a quantum system? If I tell you some, classical mechanics, how do I get corresponding quantum mechanics? So this is not a logical procedure, because quantum mechanics is the fundamental subject from which we derive classical mechanics. But always while working, the way we work is we say that, okay, we observe classical systems, and then we say this is the quantum theory corresponding to it. These are the operators and so on. So how does one go from one? So there is no logical way, because quantum mechanics is more fundamental, but usually what we do is there are some algorithms that we use from going from classical to quantum, and then we try to see if those match with experiments, and if they don't match with experiments, we are in trouble. But usually, for all purposes, for simple systems at least, these algorithms take us from a classical to quantum system. So the idea is, so we identify, so one of them is so we'll learn two of these in this course. One is the path integral, and the other is the canonical quantization. So let's talk about canonical quantization. Here the idea is to identify observables which are canonically conjugate to each other in the Hamiltonian language, and then we make them then we make those as operators. Okay, what do I mean by that? Take the simple harmonic oscillator, write down the Hamiltonian classically, and it also looks like the same. So this is the classical Hamiltonian, and from here we know that there are these if you have studied some Hamiltonian formalism, there are conjugate variables, canonical conjugates. How do we derive them? One is Px is given by del H del P, and let's start with the Lagrangian. And so in this case the Lagrangian is half mx square minus half m omega square x square. And here we identify one variable, which is the main variable, which is x. So x is here, and the conjugate of x is given by del x dot, which is called its momentum. So then this momentum becomes, in this case, m x dot, and then we can write the Hamiltonian, which is what I had written down before, p square by 2m plus half m omega square x square. And then if you know the canonical Poisson bracket formalism, it's not necessary to know for this, but we can define something called the Poisson bracket in Hamiltonian mechanics, and the Poisson bracket of two fields, any two variables f and g, is given by, I think, something like this: del f del x del g del p minus del g del x del f del p. And then for p and x, which are our main conjugate variables, we start with x, we define p, and for xp this is 1. And so the way to pass from this to quantum mechanics is to put these operators, give them hats. So now these are operators with the commutation relation xp is equal to IH bar. Okay, so this becomes this. This is how you go from classical to quantum mechanics. So what is the algorithm? First, start with a Lagrangian. Some Lagrangian will be given to you, what you want to quantize. You want to identify the momentum by del L, del X, or if it is a field, it will have some different line, del S del dot, gives you momentum, and then you are done basically, because once you have identified P, you know XP. So now in quantum mechanics, you can pass to quantum mechanics, by putting xp equals IH, and you have also the Hamiltonian from this. From the Lagrangian you have the Hamiltonian, and in the Hamiltonian also you just put hats on everything and you get the quantum Hamiltonian. So in some cases this this will not give you the usual mechanical momentum. You may not have the mechanical momentum here. So for example, if you have a system particle coupled to a electromagnetic field, particle coupled to an electromagnetic field, you will find that this P is no longer equal to mx dot. So it need not be the usual mechanical momentum, it can be some different thing. You just have to write down the Lagrangian and identify whatever P is, and then the Px thing will be corresponding to that, whatever is the momentum. So first you have to write down Lagrangian. So what is the Lagrangian for particle coupled to a electromagnetic field? Does anyone remember? Yes? So it's something like, I think, x dot minus E into A square by 2m plus Vx or something like that, okay? And then you find that the momentum, when you differentiate this with respect to, this is the kinetic term, and when you take del L del x dot, this is no longer just mx dot, so this is not so m. And then your momentum is something like x dot minus Ea, right? So this is not the usual thing, but this P is the one which you would have to use in quantum mechanics. So this P, which is not x dot but Px equals IH. Okay, so this is the algorithm, the canonical quantization algorithm for passing from classical physics to quantum mechanics. Okay, and we will also use this in quantum field theory to construct quantum field theories. Okay, so any question? No. Okay, so tomorrow we will study more about systems with more complicated harmonic, systems which are collections of harmonic oscillators, basically a first example of a field theory. And then we will do some relativity and then start with quantum fields. Okay.